Hello and good afternoon. My name is Peter Arbor. I'll be the moderator for session 2. And I'm just going to read out some notes. I'm going to read the speaker bios because they're very informative, and I know you don't have them sitting in front of you, so you may have seen them on the internet, but I'd like to give you that information. We're talking here about facade renovation and the urgent need for carbon and cost-effective strategies. Improving the performance of existing building stock in New York City is necessary to meet the city's carbon goals. The required deep energy retrofits necessitate significant upgrades to existing facade systems. Many curtain wall retrofits to date involve demolishing the existing facade system and replacing it with a new one. This practice is expensive, highly disruptive to ongoing building operations. It is also embodied carbon intensive. The critical time value of carbon further challenges this replacement strategy, yet few curtain wall retrofits to date have considered embodied carbon. What are the potential citywide impacts of this facade replacement strategy as opposed to others? What alternatives might be more carbon and cost effective? The session here is exploring current facade intervention practices on existing buildings, what drives the practices, what is the level of their effectiveness, and potential alternatives. Our speakers today are Dan Shannon and Carmen Johnson from Moed de Armas and Shannon Architects and Sam Mason from Schneider Electric. They're going to speak largely about the 2 Penn project. Dan, in addition to being by far the best looking guy in the room, serves as the managing partner at MDAS Architects in New York with nearly 4 decades of experience. 4 decades. Dan provides creative and innovative solutions to complex architectural challenges. His commitment to the philosophies of modernism and urbanism enlivens his projects with integrity and character. He has worked alongside international developers to oversee the construction of more than 50 million square feet, including large-scale curtain wall projects such as the reskinning of 330 Madison Avenue, the ground-up construction of 510 Madison Avenue, and the redevelopment of Canada's tallest building, Toronto's first Canadian Place. Dan is currently working on the major repositioning of New York's 2 Penn Plaza, the historic 1100 Avenue of the Americas, and the landmarked McGraw-Hill building, all technologically advanced facade projects. You can hardly walk around without seeing Dan's work. Carmen Johnson is a senior designer at MDAS Architects, whose design and communication skills have been integral to the success of 2 Penn Plaza and the surrounding Penn District Plan. She brings 5 years of New York City industry experience to her role on the project and has contributed both to the design and construction of every aspect of the building, including the 10 distinct facades within the project. Also with us, Sam Mason is a senior energy engineer at Schneider Electric and strategic advisor at Encompass Energy, LLC. He provides energy analysis, code assessment, and design assistance services for public entities, developers, contractors, architects, and engineering firms across North America, Europe, the Middle East, and Southeast Asia. He has 15 years of experience in the design and construction industry with a focus on pragmatic approaches to energy efficiency and sustainability. His expertise includes building retrofits and detailed HVAC design, and he is an expert in the whole building energy simulation and optimization. So I'm going to invite Dan and Carmen to present their slides, and then we'll have some questions within the group up here on stage, and hopefully we'll get a little time to take a couple questions from the audience. Thank you.
He deserves a lot more than $1 for that introduction. Hey, that was spot on, Peter, and we hope we can fulfill that mandate that he outlined. And when Mick asked us, and we miss Mick not being here, but when he asked us to consider giving a chat about recycling on these overclads, we thought, well, that makes a lot of sense, right? And Then frankly, as we started to pick it apart, Carmen and Mike Zaworski and I, we realized that we'd been working a little bit too intuitively and without enough, pure research on this and deliberate planning. And what you'll see here is that we found some good, and we found some bad, and we found some areas where we as an industry, designers, contractors, engineers, on and on and on, suppliers, we need to do better. And that's what this is about, in a sense. And we hope we can peel back some of the layers of it and see if you all have some thoughts about that and how to make it better, because as we learned in the previous one and on, we in this room and throughout are fighting a real battle. And here in the city of New York, they progressively followed California and created some regulations that we groused about, but we have embraced. And so, as Peter introduced, everything we do has the re-word in it. I don't like the re-word, but it, renovate, it, novus is the Latin term for new. And there was a lot of baloney in looking up the etymology of this, but it comes to new again. And there's a nice quote that Carmen came up with there, but the true thesis of this came from our clients. We don't want a renovated building, we want a new building. And where's that come from? The enormous capital that is put into these buildings to take them from 1960, 1950, 1940, 1910 to the current market. And let's put aside what it looks like, how it's behaving, how it's performing, how it's doing in the market. We want a new building. That is the thesis we constantly hear from our most progressive clients. This slide shows the progress of regulatory institutionalized thinking around carbon and energy, and a little bit about the progress and innovation of glass, and a lot about how we were doing our work. And you can see where LEEDs started, and then as it progressed to the new local law 97, and on and on and on, and how we originally started. Mike and I started the first reclad that we did on 430 Park Avenue, a 1928 building turned by Richard Roth into a good office building at the time, and then we took it to its next level, and the other day we were asked to renovate again. So new again, I guess, on that one. But as you progress through these selected ones, you get to more and more progressive ways to do this that align with what Peter is talking about, and that is preserving carbon and lowering energy costs. I put these three up there real quick because somebody asked a question, how good is stick-built systems? And our answer is pretty damn good, or good enough, because Richard Roth's green curtain wall that you see in 430 Park, Mike figured out with Joe Blanchfield a way to insert an IGU unit into the old curtain wall, and we fully renovated. Because of historic reasons, we liked that fact that, next to the Lever House, there's this wonderful green spandrel glass classic 1950s thing, and Richard was still with us, and he could come back and cause some trouble on our end. But anyhow, that was all with the existing stick-built system. 330 Madison, we've talked about on other times, we used that existing stick-built system to attach completely the new curtain wall on that building. So that was recycled. And then currently right now at Penn 1, which is nearly complete, is the complete reglazing of that building for triple glazed glass using the existing stick-built system there. So, and there's a lot of complexity in that, that again, we can attribute to GMS and Mike Zaborski, but really unique reuse of that curtain wall system and a little bit of welding on the existing anchors. But I just don't wanted to touch on that one. But as we grow up a little bit bigger, we're going to use Penn 2 as a case study on that. And the overriding theme on that was place, people, performance. Create a district that is east of the Hudson Yards. Bring the island back a little bit towards its center. People, best in class workplace and major public spaces to serve all the needs of the commuters and the Rangers fans. Go Rangers! And performance, oh boy, but and performance better than new. Again, that was a mandate from the chairman of Vornado, the owner, and our client on that. What were the goals? Get it to platinum, exceed local law 97, who wants to pay the penalties that are coming in 2035. That's just money out of owners' pockets, and minimize waste. We threw that one in to coincide with what we're going to talk about today. So this is the great waste right here in front of us. Real quick history lesson, 1910. We know that building came into being by Cassatt, the president of Penn Station, and within 50 years, right, it was deemed to be obsolete, ended up primarily in the Meadowlands, as you see in that famous picture. And it was an enormous misstep by the people in power at the time. And we put this slide in because it proves how wrong it was. Grand Central Station, a little bit older, but a major transportation hub, is the reason why there is so much economic vitality in that corner, in that center there. And we all know what's going on around all the super talls, all that investment because of Grand Central. Not because of its air rights, but because it's a transportation hub for half of the city, the other half being the west. So again, if we're talking about saving, let's start with the waste. That's the building that was. There's an outline of the building that cannot be explained. It really, really can't. I have a friend of mine that said, why do architects make brown buildings? And I'm like, there's no good reason. just no, bricks aren't even brown, they're red. So, but you can see, 1.4 million square feet. It doesn't connect to the city. It has no public space, and it doesn't entitle the people who are coming in from all points or going to the venue there, and it has horrible window condition for the workplace. 2023, November, this will be completed, or anybody with an MDS badge on will not be allowed back into the city. 1.5 million square feet with 56% visible vision area in the building in terms of that. And the goal on this thing was to reconnect the building to that neighborhood. What you see in front is the addition, which is 430 feet long, 50 feet off the ground, 70-foot free span, 25-foot floor to floor. And one recycling note on that, all those silly little columns are actually loading on the existing Penn Station, the original Penn Station foundations. So, and without that, this project was not possible because we can't stop the trains. And so that was a gift that Brian Falconer and Severud were able to figure out after many, many sleepless nights. So what we're going to talk about today as a case study is what we used, what we left behind, where the stuff that got taken off went, how much of the embodied energy of the building brought value to it. Sam will talk about in depth about the energy analysis and all the savings around that, and then finally what value the building recreated in the community. And with that, I'm going to turn it over, if this is the right time, Carmen, to my colleague Carmen, who has really dedicated herself to this project.
So as you can see here, the existing curtain wall at Penn 2 is characterized by gray tinted single pane glazing and alternating vertical stripes of precast concrete panels and metal panels with a thick glass spandrel at the floor slabs. The precast concrete covers perimeter columns, while the metal panels cover a high-rise, high-pressure riser mid-bay. And our overclad design introduces a curtain of reflective glazing with a slim metal channel and stack joints at every other slab. And this creates better proportions and a modern appearance for the building. And the triple glazed system alone increases the efficiency of the building by 6%. And it opens more opportunities at the interior as well. So the thermal insulation gained by the new curtain wall design allows for the MEP systems to downsize, which means we can remove that existing high pressure riser and the existing induction units and replace it with a low profile FCU. And that results in 43% increase in vision glass on a typical floor. And so you can see the increased quality of space and daylighting that we can achieve on the existing office plate compared to what's on the left and the rendering on the right. So if you take a walk down 7th Avenue today, you can see how this transformation takes place, is how it's achieved in various stages across the facade, but what you don't see are the logistics of construction and the numbers that are driving decision making. So here's what exists. It's the single pane glazing, vertical precast and metal panels, and glass spandrel. The glass spandrels come off first in the initial stage and are replaced with a back pan and new curtain wall anchors. So in preparation for the new curtain wall, we conducted a study with our curtain wall consultant, GMS, to determine how structurally viable the existing mullions were, and the findings allowed us to utilize their inherent strength to design a new anchor system that actually latches onto the existing mullion while reaching back to the building's structure and then projecting out to receive the new curtain wall. So rather than sending all of the existing frames away to landfill or to recycling and building a new system, this solution touches the existing facade lightly and reduces waste while allowing tenants to stay in the building longer, for a longer period of time during construction. We decided to leave the precast panels where they were for the same reasons. Costs would be high, logistics would be complicated, and tenants would have to leave their office space for a much longer period of time. We're also reusing steel beams, steel columns, concrete encasements, and the concrete slabs of the building, which have a massive amount of embodied energy within them. And so rather than tearing these elements down, renovation respects the carbon footprint that already exists on the site through the history of construction here. Then the new curtain wall gets installed in front of the existing cladding. So we're using a triple glazed IGU 1 9/16 inch thick from Interpane. It has a U value of 0.14 and a solar heat gain coefficient of 0.3. Soda Wall is our curtain wall fabricator and WW is installing. And this decision to go triple glazed creates a ripple effect of increased efficiency for the building that we'll get into a little bit later. So you can see at this transitional stage, there's still a lot to be removed from the inside in order to achieve that vision area ratio that we saw earlier. And so like Dan mentioned, Mick asked us, where does all of this removal go? And we wanted to learn as well. So we teamed up with Turner to track it. So the metal induction unit covers can be 100% recycled, but the drywall enclosures, tenant ceilings, and carpets will all go to landfill just due to cost efficiency during demolition. And we wonder if there's a way to make recycling these products more economical in the future. But the existing concrete slab and beam encasements reveal a turnover condition that's inherently clean and modern, and that maximizes the impact of the increased vision area, which you'll see here. So the CMU that's behind all of this is an asbestos-containing material, so it needs to go to landfill rather than being used for backfill or roadbed if it were clean. But the high-pressure riser and the metal panel that concealed it will be 100% recycled. Then the existing mullions that remain in front of the new vision area are cut and recycled. We know that aluminum is currently the most valuable recycled metal due to its versatility. But 100% of the glass will be sent to landfill. And that's because it's not currently cost effective to abate the coating that prevents it from being converted to pozzolan. Pozzolan is the stuff that glass bottles and recycled glass is made from, and it needs to be clean of adhesives and coatings. So some 50s era curtain wall systems with single pane uncoated glass can be cost effectively recycled because both the frames and the glass is viable for recycling. But 70% of the 440 million square feet of New York City commercial space was built before 1980, most of which is going to have to be renovated because of Local Law 97 carbon caps. And so that means a lot of coated glass is going to be removed from these buildings. And the industry needs to respond to that. So how can we incentivize the work that's required to strip the adhesives and the coatings from these IGUs to make them recyclable? We admit that this is a secret of the construction industry that we don't have an answer to yet. But we have learned some lessons over the years about keeping things from the landfill that can be used in the future life of our buildings, and that's why we designed an overcladding system that utilizes the existing mullions. That's why we're leaving as much of the building in place as we can. And we're also reusing the rest of the perimeter piping to service our new low-profile fan coil units, which are 1 foot 4 inch above the ground and a little over 2 feet back to face of glass, and that's 10 inches lower than the former induction unit. So not only does this contribute to increased vision area, but fan coil units create better zone control and operate more quietly and efficiently. So the result is a highly efficient building envelope that allows this building to become new again rather than having to build new. And so I'm going to turn it over to Sam now. He's going to describe the evaluation of this building, which directed ownership and the design team towards these decisions.
We've already seen this graphic before today, and I'm sure you'll see it again in the other presentations, but buildings account for 40% of carbon emissions, both from an operational and a construction, both materials and construction actual emissions. And what does that mean for us as the professionals in this room? What can we do about that? There's really three things that we can sort of do to deal with carbon emissions. One is to reduce the emissions, which we all understand, we'll talk about. We can sequester the carbon, embodied energy, which we're talking about today, and then cooling the planet, which is the smartest, engineers and scientists out there. We won't talk about it today, but capturing carbon, doing other things. So, in reality, what we're going to talk about is those first two items. How do we reduce emissions? How do we sequester the carbon? So, a little bit of background. I'm sure everybody's familiar with Local Law 97, but if you're not, coming up in 2 years, there will be fines levied based on the carbon emissions of your building. And then in 2030, that'll get much more strict. And you'll pay $268 a ton of CO2 equivalent. So for some buildings, like you'll see for 2 Penn, that was a fairly substantial fine from the get-go, and it was part of the driver for why they basically engaged us and went with this much more high-performance facade. So I guess this slide is basically just to talk about strategy, and we always like to think about this from a load reduction point of view, that needs to be your starting point. Whereas a lot of projects come in and they just want to replace mechanical, just want to do the best new chiller that you can get, new heat pumps through VRF. That's all great and that's all fine, but if you still have really high loads in your building, in many cases, those new solutions won't actually be able to have the capacity to service your building. So really you need to look at reduction, both from a load point of view, whether it's facade, whether it's lighting, which we'll talk about, recovering energy, which again we'll talk about today. How did we actually recover thermal energy within the building to improve performance? And then this last one, which again is not necessarily part of this conversation, but with the intent that the grid in New York will be less carbon intensive. By 2040, they want it to be carbon free. I've heard that 80% is roughly where they think they can get from an economic point of view. But let's say it is less carbon intensive in 2040 than it is today. An electrified building will have less carbon emissions, even if it's the exact same operation. So that's sort of the next step. We're seeing a lot of interest in that now. We'll talk about it a little bit in the discussion as well. So what does this look like for our analysis? So we were called in 2019 basically to figure out what is the impact of this renovation project in terms of carbon emissions, and what does it look like for local law 97 fines. And again, this is going to be really hard to read, but I'm just going to read it out. They pay roughly $5.6 million a year in utility costs, and their fine was roughly 10% of that. So on an annual basis, starting in 2030, they were going to pay $560,000 a year, based on their current operation in 2018. And how did we arrive, sort of at our baseline numbers? That's just straight utility bills, right? There's no analysis done there. But in order to give them, the client, a direction and a confidence in making these changes, making these facade changes, mechanical changes, other things, we built an energy model, which, again, probably most people know what that is, but in this case, it's a calibrated model. So it's a whole building energy model that reflects the actual operation of that building, in many cases to an hourly profile. So we meet, various requirements of ASHRAE Guideline 14, which basically says you have to meet certain accuracy requirements for your model. And yeah, again, it's a whole building model, many months in development. Again, a lot of buildings wouldn't necessarily go down this path, but this is a very large intervention. And it was something that Vornado was, they were really keen to not only use this model for the facade, but also to look at all the other components that were going to have to be upgraded as part of this project. So starting there, let's say roughly there to 83 kBTU per square foot. So pretty typical for an office building, but they're still ending up with a fine of $560,000 a year. So the first iteration of this, Carmen alluded, we're already at a triple glazed system, but the first iteration was double glazed, and that's sort of where they started. And that was the first iteration of models. We looked at 8 different glass systems and different framing systems. And the best sort of option there was getting that fine down to almost zero, so roughly $20,000 leftover bit of fine, which was great, but it was not Vornado's ultimate goal. They wanted that number to be zero. And so that's sort of what led to the impetus of how do we get to zero? And that's where the triple glazed system came in. So we ran another 4 iterations, 4 different framing systems, and that ultimately got them to zero. What's critical to note here is that we added a lot of glass, right? This was going from a 28% window to wall ratio to 56%. So we're adding a lot of glass. We're also adding roughly 100,000 square feet of building. So, that's a substantial sort of increase in footprint that you have additional loads for. But the overall scope with GMS, with MDAS, we're able to reduce the overall transmission from the existing case to our current triple glazed with that much more glass by 32%. So that's sort of a key metric, that we could almost reduce it by 1/3 just through the facade intervention. And so again, this includes some of the other tenant-related items that we'll talk about a little bit, but roughly a 20% reduction with facades and some minor tenant improvements. So that eliminates their fine, with some minor sort of items that are affected by leasing and the facade. But then there's also the whole other side of this building. We're doing a major HVAC renovation as well, which again is being staged. As Carmen mentioned, fan coils was part of that solution, right? So the existing systems here are high pressure induction units on the perimeter. They have 14 inches of static pressure at the perimeter, like very, very high, constant volume. fairly inefficient mechanical, both a mix of chilled water and absorption chillers and steam heating. So, the first step was sort of look like, what if we just did a new induction unit, made it low pressure? It actually didn't solve a whole lot for us because we were adding that much glass. And again, the step through here is a little bit out of order, but from a carbon emission point of view, this is the big picture. Induction units was not going to get us there, right? And that was, the next step was to go to fan coils where we can reduce fan energy, we can use a much smaller fan coil, much lower profile fan coil. The capacity on those was roughly 2/3 of what the existing induction unit was, so we were able to reduce that down substantially. So that was another sort of 6%, and if you add that into the glass, plus the tenant improvement package, that's what we're getting is to this roughly 28% carbon emission reduction. I will harp on the tenant piece a little bit. I know this is not the forum here, but that is the other critical item, right? Is that the tenants, they're the ones paying the rent, but they're also the ones that are consuming the energy in the building, right? They're turning the lights on, they're plugging in their computers. Without the engagement from the tenant and without a tenant improvement package, you're not going to get this level of performance. And again, this is still theoretical, like we're modeling, right? But we ran thousands of iterations of this, and this is sort of where we ended up. This is what's going to go to leasing. So when new tenants sign in, there will be a list of things that they have to meet that are energy efficiency measures for the tenant. So that is integral to this. We can affect the facade, we can affect the MEP, but ultimately, it's the tenants that are going to drive it as well. So like I said, 28% overall increase in efficiency, 35,000 MMBTU saved annually, so fairly substantial number. And that's 328, I guess roughly 328 single family homes for a year, so quite a bit of energy. And Dan, I'll leave you the last.
Sam, thanks so much, and it was a pleasure working with you. We didn't have to understand the numbers, we just had to be told at the end, triple glaze and go to fan coil units, so our job was easy. But there are some big numbers before. So what's 2 Penn new again mean? It's 460,000 square feet of new curtain wall. It's 100,000 square feet of new building. It's an auditorium for 280 people. It's 75,000 square feet of accessible outdoor space. It's a new Penn Station entry by Foster and Partners that we're building, and it's a new urban public plaza space, Plaza 33 on 7th Avenue. But what makes our client happy is the number that Sam's put up there. All of us know that a sophisticated new office building in New York City, including the removal of the existing building, we're not talking about land costs, is $1,000 a square foot. 2 Penn is running right around $660 a square foot, I believe, so that's a $400 million saving in leaving the building. If that's not enough to convince our clients, I don't know what isn't, as long as we get a high performance building from it. But the other savings in the carbon emissions and landfill are something that definitely factors in to all of our thinking today. And as Carmen very well pointed out, there's work to be done on this. We're going to follow those trucks over the George Washington Bridge and try to limit the amount of glass going to landfill for certain. But before questions, just say that Penn 1, which is nearly complete, and you should go visit. The first 2 floors are open to all of you in the building as a new kind of approach to the use of buildings in a very open and public manner. And Penn 2, as I said, will be done in 23, and they're the anchors for the redevelopment of the Penn district. Thanks a lot for your time, and Peter, if you have any questions?
all kinds
Oh,
of-
last
all kinds of
thing.
questions.
Thank you to that entire team. An amazing 5-year journey on this. All of Carmen's career to date, which is remarkable, but a enormous team effort led by Bernardo with a great focus.
Thank you. Thanks, Dan. Thanks, Carmen and Sam. Thanks. This is really like right in the spot where we're going to have way too much to talk about. We have some minutes here to cover the issues that were brought up, and they are many, and all of them very pertinent, I think, to what this day is about. So thank you for that. I want to let the audience know I have also had the pleasure of working with Dan and the MDAS team, and I've been very proud of the work we've done together, and very happy to have had the privilege to do that. So I was not involved in this project, but I've done others that reflect these principles and the approach that they have to existing buildings, which is, in my experience, quite unique and very advanced in terms of where the architecture community is at. So they've given me a few easy questions to ask, and then I've got a whole lot of other ones, and hopefully we'll have time for a couple from the audience as well. The first one is about future retrofitting. So I'll allow you guys to choose who wants to speak about this first. But when we're talking about modernism, buildings built in the 20th century, and bringing them sort of up to speed to where we are now, presumably in another 50, 60, 100 years, we're going to somehow have to do it again. I mean, even in the example you brought up at the beginning about being called back a second time for an existing building, how do you see that evolving? Is there an evolution there? Is there a way to envision doing the kind of work you do without, tearing down buildings?
I'll go very quickly on that, and then Carmen, Sam can add into that. That's a difficult question. Buildings used to be built for a 30-year life cycle, or at least the ones we're familiar with, this kind of 1960s and 70s curtain wall buildings with a lot of tape and sealant. You could get 30 years out of them. They've far exceeded that. We're building toward a 50 for sure on this, but something's going to come along and show deficiencies here, and we're going to have to address it, and I'm not certain of that. The one thing I'm certain of in New York City is there aren't going to be that many office buildings like this. These are going to become something else, and that's one of the things I think the work we're doing allows. This building at any time could become a hospital, a school, a laboratory. I can't tell you how many buildings we're looking at residential conversions right now that you never would have thought of. And I think that mix of adaptive reuse is the future of this magnificent building stock we have, the largest in the country. It's bigger than all the states, except for California probably. So it's remarkable. But we did talk about some ideas of trying to bring who knows what's coming. I'm sure you got questions on that. We already know what's in the works, and a lot of you all are working on some of those new products. And if we were 5 years behind, or we're starting now, we'd probably be considering some of those. But I think on big picture, I can't tell you how to reclad right now, but I can tell you in big picture, buildings like this won't be office buildings forever. There will be changes in their uses. Do you have anything to add?
Yeah, and I think it's important to note that we've learned lessons through this work about, stick built, like you mentioned, is easier to work with when we have an anchor system and a mullion system that's structurally viable to do a reclad like this. So designing systems that we know can easily have a window replacement or another clad go on top of it because it's got the framework there and the structural viability to do that is a lesson learned.
So that leads me to think about space, conditioned space, shelter, you know, the basic uses of or need for buildings and what they do for us. Is our goal then to try to create something more generic or something, certainly you mentioned flexible, you know, as architects and when you're in conversations with your client, can you raise the fact that, you know, this auditorium might be used for something completely different in the future? And what does that mean for the nature of a building? When you're building an office building or a residential building, what does that mean when you, as the architect?
Yeah, so the 4 books of architecture did not include the word generic in it, so.
I didn't
That's a very good question.
Say, yeah.
Flexibility
Flexibility.
is absolutely a very certain part of that, and flexibility comes through innovation, ingenuity, and creativity, and I think that will, you know, you can imagine a building and they're being done, you know, where we take out a couple of floors inside the building and move those around, and we're displacing area in New York City to create better space in the building, and it's being displaced. It's not being, you know, removed, because if anyone talks about removing zoning area in New York City, once again they're asked to leave. But I think flexibility is the issue. MDS likes simple forms, so we just stand on that simple issue. You know, keep it simple, and somebody stupid could use it later. But that doesn't mean there aren't a lot of other far more progressive buildings that are far more innovative in their forms and in their systems that can't be progressively adapted.
Can you talk a little bit about what you've learned on this project in terms of what are some of the important innovations that are presently available on the horizon, things you imagine being used on the next job?
You got that one, Carmen?
Yeah, I can speak to that. So we're definitely interested in vacuum insulated glass, which I'm sure all of you are. Much thinner, same energy efficiency, U value of 0.058 we're looking at. In some circumstances, it's 5/16 of an inch thick. And that's just 2 lights welded together to create the hermetic seal with the micropillars between them. And so we really see future applications for that in window replacements, especially of single glazed curtain walls, for a 1-for-1 replacement, and without having to increase weight or size, like triple glazed IGUs. We're also seeing big improvements in dynamic glass. So quick response times for atmospheric changes actually have a big impact on operating costs, peak power demands, et cetera. So we're excited to see how that comes down the line. Also I think Sam can touch to some energy production within buildings.
Yeah.
Can you speak to that?
Sure. So I know everybody's probably seen, you know, facade integrated with PV and things like that. I think there's been a resurgence. We're seeing a lot more ask for it, not necessarily in vertical, but where we have, you know, more horizontal or potentially sloped glass surfaces, where we're seeing a request for that. A lot of times in skylight renovations, things like that. In New York, it's not a great production value. You know, there's lots of shading, there's lots of shadowing. But I'd say even in addition to that, we're seeing a lot of requests around energy storage. And I think that's where we're gonna see a lot of push, particularly when we're looking at electrified buildings, that we're gonna have to have a way to store energy on site. And right now you can't do that. The local code and zoning won't allow you to do it within your building. So there's gonna be some changes that'll have to come for that. We're looking at several projects right now where we're looking at actually, you know, will Con Ed let us buy electricity from the grid to store that we can actually then burn later. So it's not actually renewably generated on our site. It's actually grid electricity that we're sticking in storage systems in our building. So yeah, I see some of that where we're trying to smooth out, you know, the demand on the electricity grid.
I think the interaction with utilities is a big deal. I mean, there's a lot of talk about how the grid will be improved. Are there things about that you're excited about?
Yeah, certainly. I mean, the whole electrification idea, right, is that, you know, it's being pushed along by all the other sort of disciplines. If we have really low loads, if we have really good mechanical systems, and makes it a lot easier to electrify. I will say there's a limitation in heat pumps at this point. I think that's sort of where we're going to end up, is that, whether it's heat recovery chillers or, heat pump chillers or heat pumps just generally, that technology is sort of, it's pushing in Europe. We're seeing some in Asia now. That, that will allow the grid to become, our buildings would be more grid interactive, if you would, and deal with that storage and the peaks and ebbs of the grid a little bit better.
And do you see that the existing entities finding ways to cope with that kind of interactivity outside of the architectural realm?
Not right now.
Okay, yeah, that's fair. Did you look at the full electrification of this project?
Yeah, we looked at 3 different iterations of electrification. So in addition to looking at facades, once we had this, this calibrated model, that is a tool, right? And so Vornado requested, hey, how can we get completely off the steam system? Like, what can we do? And it's a huge lift, right? Because there's those coldest days when heat pumps are the worst performing, that you really have a really tough time, and you're actually looking at electric resistance, right? We're going back to the 1970s. These buildings that were built before I was born, in the 70s, that were just electric resistance, and that's what it was. And that's what we're talking about, electric boilers. Like, that's sort of where we ended up, and we looked through, various permutations of that. But, for a building like Penn, there's not enough roof area to put enough condensers for heat pumps. There's just not enough space, right? And so for existing buildings, it's a little more difficult. I will say there's going to be some innovation. People will figure out how to do this, how to make bigger heat pumps. My colleague Andre is here from Quebec. In Canada, they're figuring this out, that they work at much lower temperatures. They have different technology there that, once it's adopted here, we'll see a push in those kinds of systems being installed. So.
Do you see the facade as something that, apart from creating efficiency and thereby kind of lowering the carbon consumption of buildings, is it something that we can expect at some point to start contributing to the flow of energy, or either through the use of passive systems or solar capture and that kind of a thing? Are vertical surfaces going to take on some of that responsibility?
I mean, you see that they are today. I mean, even with the first presentation, right? And that's vertical and horizontal surfaces that are part of, that microclimate that's creating a better condition, keeping the glass warmer, reducing sort of your heat transmission. Yeah, I mean, it certainly will. I guess the other point that comes up is resiliency, that we end up seeing the ask, like a triple glaze system on a building. If the power goes out, that building is going to stay comfortable conditions for many more hours than other buildings, right? So there's, I see that as sort of another cell that
That's important. That's very important.
that,
Yeah.
so
I guess my interest in passive systems comes, if we go back to that first presentation, we're looking at a triple glazed unit with 2 mechanical sunshades embedded in it, and to me that's not passive. That's not a simple solution. Let's put it that way, right? Are there things coming around that are less high tech, less demanding, less likely to break?
I think all of us are, New York City is very difficult, you said, because of the shading and stuff, but it's very funny. We're recently studied, sun shading on the significant facades with the greatest exposure. And, we all know here that they're technologically difficult, to burden a curtain wall with more gewgaws hanging off of it, that collect ice and fall on people and penetrate and, do all of that. But it's very interesting that New York City code on projections was really written about traditional architecture, right, for cornices and lintels and so on, and we've been using those for our career, the 10 square feet for every 100 square feet to project out beyond the building line and so on and so forth. And now we're using those to look at sun shading devices and so on. But we were all very excited about, the electrical creation on the curtain wall, and I think we all as an industry lost interest in that, and as Sam says, it's going to come back, and we know it's part of our future. We studied it seriously in Canada, and you know, once the client started listening, but then when he saw the product at hand, he was enormously discouraged. But we need to revisit that.
Modernism, being a modernist, or looking, and the legacy of modernism, which is what you guys are really engaging with, I think, is an important thing to talk about. If we have 30 seconds more, can you say in 500 words, when you sit down with your client, your international developer, what is driving these decisions in the marketplace?
Well, I want to go back. I'm going to take this somewhere else, because we can have the same discussion here on traditional buildings that we've recreated that look like what they did in 1930. We're doing the McGraw-Hill building right now, one of the great modern monuments of, you know, the 40s, but equal 410 10th Avenue. It's a fascinating, with Peter, we did, it was a masonry, concrete and masonry building, and it's still a concrete and masonry building, and it's the most distinctive building in Hudson Yards because it's not a curtain wall building. So we constantly work with our clients and saying, what is the heritage of this building? What has it contributed to date? And why are we throwing that away? One, it's distinctive because it has some beautiful traditional architecture. It has great floor-to-floor heights. The windows are crap and need to be worked on and increased and so on. So modernism isn't the play here. It's energy. I mean, it's engineering, design, construction, and so on. And sometimes they're glassy buildings, and sometimes they're masonry buildings that get revived. We all know of that 440 million square feet in New York City, only a percentage of that is curtain wall buildings. And as we fly over this beautiful city, we see predominantly a masonry city. Now, I'm not talking about, as an Irishman, bringing back the brick, because that's got fundamental issues, but preserving them and never doing a cavity wall system again is something we're really excited about. Thank you, Peter.
Okay, thanks everybody. We're out of time. Okay.